Hi everyone, I'm Joe. This is Ryan, and this is Kyle. We are representing for Team Nicaragua. We're talking about Gate 2 design process. So Nicaragua's mission statement is that we aim to empower various communities in Nicaragua by designing and implementing sustainable water solutions. With this in mind, we are working with Rancho Los Alpos Ecolodge, which is an ecotourism ranch dedicated to environmental education and community outreach. We are specifically working with Alma, the owner. We have met them with our previous trip down there. We stayed at the ranch for a little while, and these 4 to 5 families commute to the ranch to use these plots of land. We are also working with Mario Espinoza, who is the community leader down there. We have Skyped with Alma, and we have contacted her through email, and we've also emailed Mario directly and through Alma as well. Mario will be overseeing the project while he's in there, as he will have input with the design as he currently does, and he'll be working with us when we're designing it. So the problem that they have approached us with is that Nicaragua has very little rainfall during most of the year. Because of this, farming is limited to the short wet season, and therefore Alma's asked us to irrigate a portion of her land. The picture on the left shows what it looked like when we went down there at the end of the dry season. You can see how dead and barren it is, while the picture on the right shows how lush it is after the rainy season. And we are trying to extend the lushness of the rainy season a bit more into the dry season. So why is this irrigation important to them? It can provide a more reliable source of food during the dry season, and surplus crops can be sold for additional income, which they need the food, and additional income for such a poor community is well needed. So design requirements of this irrigation is that we are going to irrigate 2,500 square feet of sesame during the dry season. Sesame requires 20 inches of water throughout the watering process, so we're going to need 15,000 gallons of water for a 6 months dry season. And the system also needs to be aesthetically pleasing because it's going to be put on the ranch's land, and they're going to be seeing it daily, and we don't want them to just see an ugly tank everywhere. So not much has really been done before. The ranch has done a sustainable farming initiative at the ranch. This consisted of a few families going out to the ranch, be given plots of land which they gardened, and at this ranch there was also an outside source, much like ourselves, that helped them with this sustaining farmative initiative. Other than that, there hasn't really been much in the area that we are working at. However, even with this sustainable farming initiative, the water scarcity still renders irrigation unfeasible during the dry season. However, in the States, there has been somewhat of a solution that they've worked out. In Clemson, there's a rainwater harvesting system that uses an inverted roof, like the picture here, which is the system, that collects this, filters it into a tank, and then uses this tank for irrigation. So based off of what has been done before, our project is we're using a standalone rainwater catchment, storage, and irrigation system to allow an extended growing period for crops at the ranch. This picture here shows what our final design will look like in a CAD mockup. So the blue circle represents our tank, while the image next to it shows our catchment system, and at the bottom of the slope, the grid lines represent the area that we're going to be farming. In order to effectively go about designing this, we have broken up into 3 sub-teams of collection, storage, and irrigation. First off, we're talking about collection. So collection requirements specifically is that we are going to capture 15,000 gallons during the rainy season, and the structure has to be safe and stable. These 2 graphs show the average yearly rainfall in both Managua and Leon. They're very close in area. The first graph, the blue bars, shows the average rainfall, while the second graph, the blue bars, show the average rainfall. These graphs just go to show the stark difference in rainfall during the dry season, rainy season, with times like June and September having most of the rainfall, while times like January have almost no rainfall whatsoever. Due to the rainfall being so little in some months, we based our rainfall off of only the 7 rainiest months, as we can't really depend on the other 5 months. So this graph shows the rainfall per the 7 months that we are using, how much catchment we will receive during each month, and the last column shows how much water will be in the tank at the end of each month if we do not use any. So the monthly catchment was based off of how much rainfall we receive, our catchment area, and a safety factor. This safety factor is basically saying, okay, with the evaporation and not all the water being collected, we're only going to receive 90% of the water that falls on the roof. With that in mind, we're going to catch 15,125 gallons of water at the end of the rainy season. So in order to effectively solve this, we have come up with a few different concepts. The first concept is a separate collection system, as you can see here. This has an inverted roof with open space beneath that can serve as a pavilion-like area. It can have tables underneath, provide a source for people to meet, and it can also provide shade. So this concept is relatively easy to build, and we've also constructed a prototype of this. While the other concept that we were thinking of is a connected collection system. It's very similar to moving this separate collection system on top of the tank and using this as a cover for the tank. However, this makes it more difficult to construct due to how the tank must be built. In order to build this tank, we have to get inside of it, and putting a roof on top of that makes it nearly impossible to do that. And also with the huge diameter of the tank that we are looking at, it's going to lack structural stability, as in the middle there will be no support for this. Therefore, we went more with the inverted roof. So after our prototype and changing our specifications a little bit, we have changed our roof angle to a 10-degree roof angle, which is much lower than our prototype. We've also changed the heights up so that the lowest point is at 7 feet, with the 7 foot being where the gutter will be at, and the highest point will be at 9.25 feet. This picture shows what it will look like with the person representing a 6-foot person. So in order to build this, we have 2 sections of roof, with each section being held up by 3 supports, and both sections will be filtering down to the same gutter. So this collection area, each roof will have 300 square feet of collection area, and the gutter will have 10 square feet of collection area. This represents our 610 square feet of collection area. In order to analyze this structure, we assume maximum loading conditions, which is a full gutter, and maximum compressive stress per support beam was 25 psi. This safety factor for all commonly used woods was 50 plus or greater. And next steps that we're working on, we are planning on working on a larger scale prototype using final proportions, and we also plan on doing in-depth static structure analysis using MassStan2 software, and we also plan to get structural engineer approval of design. We have already worked with a professor to get some input on our design, and in order for him to fully approve it, he wants this full in-depth static structure analysis, but he likes what he's seen so far. Now in storage.
All right, so I'm Kyle, and I'm going to be talking about the storage portion of our system. So when we were designing our storage portion, we had a few requirements we had to meet. First, we had to build a tank that could hold 15,000 gallons of water for use in the irrigation system. This tank had to be structurally stable both when the tank is completely empty and when it's completely filled up with water. We needed to minimize the amount of contaminants entering the system that would be coming from the collection system and roof. And then we also needed to minimize the growth of bacteria or other contaminants in the water once it's in the tank. And finally, we needed the tank to be aesthetically pleasing for good integration into the community. So when we were first thinking of concepts for the tank, there were basically 3 options. We could either go with plastic tanks, a concrete tank, or a tank made with walls of corrugated metal. Our original design included a concrete tank with a solid metal roof for best structural stability. It also, to increase the structural stability, we're going to divide it up into 3 tanks, and then we would include a vertical first flush system to take out any contaminants entering the system from the collection system. After researching a little more and talking to some sources in Nicaragua and tank building companies around the US, we decided that we could build a structurally stable tank with all of the water in one tank. And we also realized that we had good access to corrugated metal, so we would build a tank with corrugated metal as the walls. But we realized that a solid metal roof would be very hard to support with nothing in the middle. So for our second design option, we switched it to a tarp roof supported by girders that would run across the top of the tank. So in detail, the first flush system is on the left. The water would come in down the top and then pour straight down into the larger PVC pipe below it. This section would fill up with a ball floating on top. Once that ball rises into the top where the PVC is skinnier, it would block it, and all remaining water would go into the tank. The idea of this is that the first water coming off the roof would have all the dirt that is built up on the roof over the last few days without rain. After each rainfall, the ball valve at the bottom could be turned, releasing all the water with the dirt in it. For the tank itself, we would dig a hole 24 feet in diameter and about a foot deep. We would then fill this with a ring of bricks around 22 feet in diameter and sand. So then we would build the actual tank with the walls right above those bricks and the sand for total support. The walls would be 6 feet high, made of corrugated metal. There would be 6 holes around the top, 1 for input, 4 for overflow, and 1 for the outflow. That's pictured at the bottom there. Each of these holes would have a PVC output with a bulkhead to connect it to the actual metal wall. The metal walls would be built out of 4 by 12 foot corrugated metal sheets with bolts used to connect them together. On the inside of the tank, we would place a tarp over the bottom of the sand, and then we would put a liner over that tarp and up against the walls to make the tank bacterially stable. The roof itself would be the girders with the tarp roof over top. So then we move on to our final design, which is after prototyping and talking to engineers. So in this design, you can see on the right, there is the first flush system, and next to that is a gutter overflow valve. The tank itself is, as I just described, still the metal walls, 4 foot by 12 corrugated metal sheets. And there will be 15 concrete blocks placed under the wall in the sand around the outside for support. And halfway in between these blocks would be the wooden stakes that are pictured here. The roof itself, we changed a little bit. We decided that the best option would be a tent-style roof with a pole in the middle cemented into a concrete block supporting a tarp roof. We will then put a belt around the outside of the top of the tank and use a ratchet to tighten that belt. So this final design would be 11 foot in radius, 6 feet in height, but the water level would be 5.5 feet at the overflow valve. This would give us 15,641 gallons. We also calculated the safety factors of this tank. When it's completely full, it will have a water weight of around 130,000 pounds. This would produce a PSI on the sand of about 2 to 3 PSI, which is minimal compared to the safety values. The wall itself would weigh around 6,000 pounds, which would produce a PSI of around 60 on the concrete blocks. This also is well within the safety valve. The biggest consideration for safety would be the force of the water pushing out on the tank walls, which produce a transverse stress of around 6,000 PSI. However, even this, when you consider the yield, shear, and ultimate tensile strength, all of those would be a factor of 10 below the safety values. So with prototyping, we ran 7 dye tests with our first flush system. So the way we did that is the dirty water portion can hold 2.7 gallons. So we put in 1.5 gallons of dyed purple water and then ran clean water through it to test to see if the ball could successfully keep the dirty water from mixing with the later clean water. And as this picture shows, it did. The water on the left is the water that was stored in the dirty water section, and the water on the right was our outflow. Today and tomorrow, we're going to build a partial prototype of the tank wall. This will both confirm our confidence that we can build a structurally stable system and help us practice the building techniques and what parts of the design are going to take the longest. And now Ryan will talk about the irrigation portion of our design.
Hello. So we'll be farming sesame. Sesame is one of the most drought-resistant crops, and it has a leafy broadleaf crop. It usually grows from 3 to 5 feet and has a 90-day growth cycle. It also grows best in sandy and well-drained soil, which is perfect for our Nicaraguan environment, also above 70 degrees Fahrenheit. Sesame has 4 stages: seedling, mid-bloom, ripening, and late dry down. The majority of the irrigation would take place at the beginning of seedling and at the end of mid-bloom. While choosing a type of irrigation, we considered these 3. Sprinkler system, which is where water is sprayed over a large area, which is great for a large crop area. However, a lot of water is lost due to evaporation. Also, furrow irrigation is where the canals in between the rows are flooded. The positive side of this is that it's well known for sesame farming. However, it is non-uniform, easy to overwater, and excess watering. Finally, drip irrigation is where water is delivered via PVC or irrigation tape directly to the root of the crop. The pros of this, it has efficient use of water. There's very minimal evaporation. It's sustainable. However, it's not practical for large plots of land. This doesn't really apply for us because we're only irrigating a 1/20th of an acre as opposed to a multi-acre farm. For our preliminary design, we have the tank at the top of the hill and then our field towards the bottom. And we have a 2-inch PVC coming from the tank down to the field, and then a T-joint from there. And then all of our rows go parallel to the slope of the field, and each row is 50 feet long. While evaluating PVC versus drip tape, we gave weight percentages to each of these categories and then gave a grade on a scale of 1 to 10 to PVC and drip tape. And there are 3 major differences here: the price, the durability, and the ease of installation. Drip tape is less expensive, however, PVC is more durable. A major difference occurs in the ease of installation. Drip tape comes in rolls and can be rolled out, cut to the appropriate size, and there aren't many joints. PVC comes in about 10-foot long sections, and there are many joints, and everything has to be cemented together. And here's our PVC prototype. We had 2 10-foot rows, and even with this small scale design, it was very difficult to manage, and leaking was definitely a possibility due to all the joints and connectors. Our final design is that we have 25 rows of 50 feet each. There are 2 feet spacing in between each of the rows, and we'll be using 5/8 inch drip tape with 8-inch emitter spacing. Overall, we have 2,500 square feet of land, and we have PVC connecting the tank down to the field. A major difference from our preliminary design to this is that we have the main PVC running down the length of the field, and each of the rows go perpendicular to the slope of the field. This allows for even distribution of pressure along the length of each row. And we have also water duration. This tells us how long we'll have to keep the water on based on 0.67 gallons per minute, which is from the drip tape information. Watering occurs the majority immediately after planting and then about a month in. Watering duration varies from 45 minutes to 3 hours and at the beginning, an hour and a half to 2 hours and 15 minutes at the second watering cycle, which lasts about 8 days. And then additional watering occurs about every 10 days until the plant begins to flower, and then irrigation stops. And also additional irrigation may be needed if the plant leaves begin to wilt. Looking forward, we are planning to revisit irrigation systems to confirm our design and see if there's anything that we can modify. Also, we need to arrange to obtain the materials in Nicaragua or obtain them in the United States and bring them with us. And we also need to plan out a day-by-day schedule of how we will construct our system in country. For the team next steps, we need to further verify design and construction feasibility, make sure everything is structurally sound. We need to continue to collaborate with in-country contacts and Aqua Clara International. And then we need to make our final plans for travel in late August. Thank you, and do you have any questions? Yeah.
So it sounds like one of the biggest problems that your system is with the amount of water you need for the harvest of the crop, you're pretty much relying on a huge amount of the rainwater actually making it to the field. Let's say, for example, your design is adopted and they use it to water the field, but during the harvest they run out of water before it can be harvested. What options would they have to fall back on if your project failed, and would those costs offset the benefits of actually having the harvest?
Well, fortunately, as I said, that sesame is a very drought-resistant crop. So even with the watering at the beginning and the mid-bloom stage, those first 2 waterings, if we couldn't water anymore after that, I believe that we would still have a crop yield. It would not be as large as if we could water it fully, but I think it would still be a successful irrigation. Does that help? Yeah.
So like in terms of implementation, when you go in country, it seems like you have a very big project. So I'm wondering, like, how would you have different trips that meet different needs, or like, what would you do in terms of like implementing it?
As far as obtaining the materials in Nicaragua or constructing?
Both.
All right, well, we are, our source in Nicaragua is Mario and Alma, and they have confirmed that they would be able to obtain some of the materials before we arrive, so we don't have to do that during our trip. And then part of our next steps is confirming how long it takes to do each of the builds and making sure that we have enough time in our travel. Do you have anything to say?
Yeah. So we also have a handyman down there who's willing to help us, and some of the families will be able to help us construct this when we get down there. So we have extra manpower more than just what we can bring.
What kind of costs are you guys looking at, and who's covering those costs?
We have, for the total cost of, I know irrigation is about $300. I don't know for storage or, you know.
I can maybe weigh in a little bit. Yeah, so we have some rough cost estimates that we've gotten from just communicating back and forth with just the amount of materials that we need. But they've been wanting a more specific design system so they can find exact sizes of things. But it's gonna be like probably in the range of like $5,000 or lower, it looks like at this point. So we're planning on covering that ourselves from money that we raise. So have you guys analyzed how the system is going to interact with like the farmers themselves? So like if the tank, if something is stuck in the tank, how easy is it to like access it and like open the top, or how the irrigation system is going to interact with the farming, or like, because normally they use tape because it's flexible, you can like walk through it.
I can speak for the tank that was one of the reasons we went with a tarp roof. Is it's not a solid metal roof. If something does go wrong, you can get in there and fix it, clean it out. And also for the first flush system, we've realized that the ball valve at the bottom would be one of the parts that would wear down. So instead of making that a regular PVC seal, we actually are finding pieces that's like a screw-on PVC, and then we would cover that with Teflon tape to make it watertight. So that way if that part breaks, they could easily replace it. So that way we could minimize things like that.
Yeah, and for the farming aspect, that's the major reason we chose the drip tape, was because it was flexible and they can move it around. Or if after the sesame farming season they needed to remove our irrigation system for any reason, it would be easy to roll up versus PVC, where once you construct it and glue everything together, that's how it is. Yeah.
What steps have you taken in order to like engage people like Mario or Alma or other community members or other families that you talked about that will actually be using the design?
Well, I believe Alma came to us with this idea of creating an irrigation system. So we've had several Skype calls and emails going with her, and so we're in pretty constant contact with her, and we're able to confirm with her that our design matches her needs and that everything that we will be building, they will be able to handle.
We've also been able to talk with the community members when we went down to Nicaragua last year. We met with a lot of the food members, and we Skyped with them a couple times this year as well to make sure that they understood the system.
Yeah.
So I like the first flush system, it looked really well, and the overflow valve, how you integrated that. Just careful with PVC and sunlight. I think there's another team that's working with PVC outside too. I think white PVC, I'm assuming it's the same thing. It's meant to be underground, and I think it's exposed. It's gonna be outside, right? Those first flush
Yes.
systems and any PVC components, they like degrade over time with sunlight. Just the thought. But I had a question about the safety factor. Was that 50 plus PSI, like your safety factor, or was that 50 times the rated load?
Do you mean for the collection?
Way back where you talked about the beam, I think, safety
Okay,
package.
so it has to be like a minimum of 50, and all of them are well above 50.
50 times. 50 times.
Yes.
50 times. Wow.
Yeah.
That's
Just
great.
good. Yeah, for just some compressive, it just takes a lot for the beams to buckle and they're not
Okay.
gonna.
Well, that's excellent, but, all right.
What about, sealing for the containment, tank? So where the bricks aren't gonna break from shear, but how are you guys sealing it?
So for the individual pieces of metal, we're using bolts to put them together. And then on the inside, there's going to be a liner. So the wall itself is not going to be the water actually in contact with. And then we're going to seal that liner to the top of the tank using 2 thin pieces of sheet metal and more bolts, almost as like a clamp. And then to seal the tarp at the top, we're going to put that over the edge of the tank and then put like a leather type belt around the outside and then use a ratchet to keep that taut. Is that what you're thinking?
I think
Okay.
As they've described before, it's much like above ground pool is how they base their design off of, where they have like the liner on the inside making it watertight.
So it's made out of like a heavy plastic then, or?
It's a special liner. It's not just like an ordinary material. It's specifically made for this type of purpose.
If your factors of safety are like 50 and over, have you thought anything about like that you might be over designing? Because you might be able to like cut back on some material that you use.
We just figured most of this out very recently, but the only thing that would be able to cut down would be 1 or 2 supports, and that wouldn't lower our cost by very much. So it wouldn't affect things very much.
So you initially were talking about some of the sustainable farming initiatives
Mhm.
on the Eco Lodge. So since it's an Eco Lodge, what sort of, there must be some sustainable initiatives already embedded within the resort to make it an Eco Lodge. So
Mhm.
have you researched what other initiatives have happened?
I don't know most about that. Mario knows more.
Yeah, so what they like, how they tell themselves as an eco lodge is that they are very, like all the activities there are very just involved with the environment. They have like horse rides around their property and like zip lines like around the slope that they have on their property as well.
Okay.
So it's not so much that they're committed to sustainability, that's why we're working with her for this project, but yeah, it's not that they have like those kind of things already in place.
Yeah.
It's more of just
Also the farming initiative that they'd done earlier with another organization was an organic farming initiative. So they had tried, the problem with that was that it was a little bit too different from the way that they normally farm for it. Like some families did stick with it, but like after the people left, it wasn't like very held on to.
And then what sort of filtration is needed for the irrigation system?
So after the first flush, once everything's in the tank, we'll only need like a typical store-bought filter that you would put on like a hose or anything or something like that, just to get rid of all the small little particles that could plug the emitters. But other than that, the first flush takes care of most of it.
So it's mostly for like debris rather than chemicals or like bacteria?
Yeah, there are multiple different types of filters, some for algae, some for particles. So we'd have to decide between those or just get multiple filters either. They would all be equally effective. Yeah.
Sorry,
Oh.
I'm kind of hogging. If any of you have a question? Okay. So I noticed that you had a design matrix. It was called an evaluation chart for the irrigation system. But was something like this done for the other 2 systems as well to narrow down the design?
So for the tank aspect, we didn't necessarily do that, but we did base most of our collection off of that prototype that we showed you that also had the inverted roof system, and pretty much anything else we had was very similar to that design. And the only other concept that we really heavily considered became too unstable and too hard to make due to the tank.
And also, we had basically 3 different options for the tank. We could either go with a lot of plastic tanks or concrete tank or the corrugated metal tank. Problem with the plastic tanks is that they would be very expensive, so we've ruled that option out very quickly. The concrete tank, while it would be structurally stable, it's very difficult to build. We probably could not build it. We would need to bring in special labor, and it would take a long time, not something we could do on a 2-week trip. It would be multiple months of complicated work to build. So we decided the corrugated metal, once we found the availability and someone contacted NicarAGUA who can work with metal, we decided that would be the best option.
And then just two more things that are somewhat related. Do you happen to have a slide with all the different forces on it that you were mentioning? I think it was in not the collection, but the storage system.
We do not have a specific slide. I mean, if you have questions, I could go over them a little bit
Okay.
again.
I don't. I just,
Okay.
maybe for the panel, it might be helpful for discussion purposes.
Okay.
And then the slope of the hill, was that something that was measured when the team went down last year, or is that?
They based it off of, they kind of eyed it out, but also we talked to Alma, and she said that there was about a 10-foot drop down to the end of the hill, which that adds into our gauge pressure. And our pressure for the drip tape that we're using, it operates between 4 and 15 psi. And the pressure with the hill and accounted for and the tank varies from like 5 to 6 psi.
Have you, two questions. One, is the inverted roof galvanized steel?
It'll be corrugated metal.
Okay. And then for the piping, have you considered other materials besides PVC, like HDPE?
Not that I'm aware of.
Oh, for the irrigation?
Yeah.
So so for the actual field, we're using drip tape, which is designed for this type of thing. But for the only PVC that we'll be using is transporting the water from the tank down to the field. So it would be easy to switch out any different type of material there.